Hello everyone, my name is Benjamin Reidys. I'm a fourth-year PhD student at UIUC. In this talk, I'll be presenting our work, RackBlox, a software-defined rack-scale storage system with network storage co-design. This work was done with my advisor, Professor Jian Huang, and collaborators from UIUC and IBM. Software-defined infrastructure is becoming increasingly popular in modern data centers. With software-defined infrastructure, data center operators have the flexibility to redefine their management policies to quickly adapt them to their specific data center needs. Software-defined networking, an early example of software-defined infrastructure, allows network operators to deploy new network protocols and reconfigure their network resources using programmable switches. Similarly, software-defined storage enables the upper-level software to directly manage the low-level storage chips and reconfigure their storage management. Due to these benefits, software-defined infrastructure has become a backbone in modern data center management and has been adopted in many major data centers. Let's first discuss software-defined networking, or SDN. In software-defined networking, we have a control plane that defines the management policies and a data plane that executes them. In software-defined networking, the data plane is responsible for operations such as routing packets and collecting network statistics, while the control plane manages these data plane operations by defining policies such as I/O scheduling and congestion control. To help simplify this management, we have the P4 language, which can enable programmers to define custom packet formats and customize their packet processing. In this fashion, we can redefine the management policies in the control plane without affecting line rate throughput and without hardware modifications. In this way, network operators can deploy customized network functions for flexible traffic management and improved resource utilization. Similarly, software-defined storage enables the upper-level software to manage the low-level storage chips. And when we talk about software-defined storage, we usually refer to software-defined flash, or SDF, which manages SSDs, which, due to their increasing performance and decreasing cost, are increasingly deployed in modern data centers. But before I discuss more about the benefits of software-defined flash, let me introduce some necessary background on SSDs. An SSD also consists of a control plane and a data plane. The data plane in the SSD performs the basic storage operations of reading, writing, and erasing data, while the control plane defines storage management functions such as I/O scheduling, garbage collection, and wear leveling. Garbage collection is an important storage function for data center management. SSDs only support out-of-place updates, so eventually, old data will consume the SSD's space. Garbage collection periodically erases this old data so that free blocks are always available to support out-of-place updates. This must be done carefully, however, as erase operations in SSDs may pause incoming storage operations and add significant tail latency. Another important feature in SSDs is wear leveling. This is because the individual flash blocks in the SSD can only sustain a limited number of writes before they wear out and are unusable. Therefore, wear leveling can help extend the lifetime of SSDs by distributing writes evenly across the underlying flash blocks so they wear out evenly. Software-defined flash opens up the SSD and allows the system to reconfigure these storage management functions. Through this customization, software-defined flash can help improve resource utilization and enable predictable storage performance. While we observe many benefits from both SDN and SDF, they are deployed in data centers separately today and managed in data centers separately today. At first glance, this makes sense because storage is typically deployed at rack scale for scalability and simplified management, but with the network connecting it. But this lack of coordination can lead to suboptimal end-to-end performance. The first place where we see this lack of coordination is in I/O scheduling. We see that both the SDN and the SDF have their own separate I/O scheduling policies. Unfortunately, the scheduling decisions that can be made for a request when it is a packet in the network can conflict with the scheduling decisions for that request when it is in the storage stack. these conflicting scheduling decisions can lead to unpredictable end-to-end performance. Additionally, separately optimizing in the SDN and SDF for end-to-end performance can lead to redundant effort and additional complexity. We also see that some storage operations, such as garbage collection and wear leveling, could benefit when coordinated at rack scale. Remember that garbage collection may pause incoming storage requests and add up to orders of magnitude delay to incoming storage operations. One observation is that storage is typically deployed at rack scale, and rack scale storage systems typically have at least 2 replicas in one rack and at least 1 replica in another rack. Therefore, to avoid the performance interference from GC, we could leverage this data replication to redirect requests away from replicas that are performing GC. Unfortunately, current SDN and SDF does not do this. One approach would be to develop a software stack that can perform this coordination. But we observe that the top of the rack switch acts as a central hub for all of the I/O requests that enter or leave the network. Given its programmability, this makes it a better place to track the GC status of SSDs and direct requests to the appropriate data replicas. Similarly, individual SSDs have wear balancing, but different SSDs may have different write traffic, leading to wear imbalances across SSDs in a rack. Ideally, we could leverage the SDN to expand wear leveling to rack scale and extend the lifetime of the entire rack by allowing the SSDs to wear out at an even rate. As we can see, there's a number of optimizations that we miss out on without coordination, which leads us to the conclusion that SDN and SDF can and should coordinate. And in order to realize this SDN-SDF coordination, we designed RackBlox, a software-defined rack-scale storage system with network storage co-design. We first decouple the functions of the storage management and integrate the appropriate functions into the SDN to enable our co-design while keeping the rest of the functions in the SDF. Using this co-design, RackBlox first enables coordinated I/O scheduling, where the SDF and SDN can provide precise feedback to the I/O scheduler to improve end-to-end performance. To avoid the overhead created by garbage collection, RackBlox enables coordinated garbage collection by coordinating across the data replicas to redirect requests to replicas that are not performing GC. Finally, RackBlox enables rack-scale wear leveling with a 2-level wear balancing mechanism that ensures that all of the SSDs in the rack wear at an even rate. Unfortunately, achieving this vision of SDF-SDN co-design is challenging. And the first challenge is how to decouple the functions of the storage management across the SDN and SDF without overly burdening the existing SDN. This is made challenging because of the limited hardware resources available in modern programmable switches, which only have tens of megabytes of memory available in the switch data plane. Therefore, we can't simply offload the storage management into the SDN. We need to carefully decouple the management and design the shared storage state. Finally, both SDN and SDF are built around programmability and flexibility. We need to make sure that when we coordinate, we do not restrict this flexibility and ease of use. Let's first discuss how we decouple the storage management across the SDN and SDF. Due to the hardware constraints in the SDN, we want to keep as much of the storage management in the SDF. Error correction, for example, is best performed in the hardware of SSDs, so we keep it exclusively in the SDF. It can be challenging for software to manage the remaining storage functions that are exposed by SDF, so we group together the underlying flash chips and virtualize them using the virtual SSD or vSSD abstraction that we've proposed in our prior works, FlashBlox and BlockFlex. The vSSD abstraction provides the flexibility to map vSSD instances to any number of underlying flash chips, providing performance isolation with a limited metadata overhead. This helps simplify the management of local storage functions. For address translation and bad block management, we observe no benefits from coordination, so we also keep them exclusively in the SDF. For I/O scheduling, garbage collection, and where leveling that benefit from coordination, we need to determine whether we should use precious switch resources to retain their state. For I/O scheduling, we determine we only need to add one packet header field, and for where leveling, it happens infrequently enough that we can coordinate in the servers. Therefore, only garbage collection requires using our programmable switch memory. And to do so, we store all of the data necessary to redirect requests. For each VSSD, we store its GC status, its replica, the replica's GC status, and the replica's server location. The first table, the replica table, maps the VSSD to its own GC status and to its replica, while the destination table maps the replica to its GC status and its location. Together, these tables consume at most 1.3 megabytes of the tens of megabytes of available switch memory. Now that we've discussed how to decouple this storage state, we need to discuss how we communicate to update the storage state. And here we leverage the ability of the P4 language to define custom packet formats without hardware modifications. And we add 3 fields to our custom RackBlox packet: the op field, the SSD ID field, and the latency field. The op field defines the type of operation for the packet, which can be management functions such as creating or deleting VSSDs, basic data operations such as reading or writing data, or updating the GC status bits in the table with a GC op. The VSSD ID determines which VSSD this packet is for, and the latency field accumulates the network delay and will be used in coordinated I/O scheduling. Now that we've discussed how we decouple and update the storage state, let's discuss what this co-design can enable, starting with coordinated I/O scheduling. When requests arrive at the storage server, they can have different network delays due to differences in network scheduling or other network factors. Here we have request 1 and request 2 with different network delays. Without coordination, the storage scheduler may first execute request 2 and only execute request 1 later, violating its SLO. So ideally, we could incorporate the network delay into our storage scheduling. So with coordination, we could prioritize request number 1, knowing that the short network delay of request 2 enables us to relax its scheduling priority. So to achieve this, we enable scheduling in the local storage using the network delay as part of the priority. Precisely, we use 3 components to enable the prioritization in the storage scheduling. The incoming network delay, which is the delay before the request arrives at the storage server, the storage delay at the storage server, and the outgoing network delay when the request is returned to the client. To determine the incoming network delay, we use the in-network telemetry available in current programmable switches, which allows us to compute the switching latency for each individual packet. We can use the latency field that we added to the packet to accumulate this network delay as the packet traverses the switches in the network. For the storage delay, we use the time the request is then queued into the storage stack, which allows us to automatically prioritize requests that have spent more time in the storage scheduling. To estimate the outgoing network delay, we use a sliding window of recent incoming packet latencies to better capture the current network state. Now let's return to the previous example. Without coordination, the storage scheduler may first in-queue request 2 and prioritize it over request number 1. Now with coordination, we would see that the higher network delay requires a higher prioritization in the scheduling, and we would reorder the requests. Now, when the storage executes the request, it would first execute request 1 and execute request 2 with a relaxed scheduling priority, but achieving the desired end-to-end latency for both requests. Now that we've discussed how we add the network state into our storage scheduling, we also want to account for the storage state when in the network. So remember that when a storage request is forwarded to a server that's currently performing GC, it may be paused until the GC has finished at that server, which can add orders of magnitude delay. So luckily, our current rack scale storage systems already replicate data with at least 2 replicas in one rack and at least 1 replica in another rack. and we could leverage these data replicas to avoid this performance interference. To do so, when a read request enters the switch, we first check the switch tables. In this case, we see that the VSSD is performing GC, but the replica is not. Therefore, we can read the destination table to rewrite the destination of the packet and redirect the request to avoid the GC overhead. Unfortunately, replicas could be performing GC simultaneously, and this may happen because writes need to be sent to all replicas for consistency. If all replicas are performing GC simultaneously, then we would not receive benefits from redirecting requests. Therefore, we want to minimize the time that replicas are executing GC simultaneously. Therefore, we enable the switch to delay the GC of certain replicas. Instead of a VSSD immediately executing GC, it will first request to perform GC. The switch will then check the GC status of its replicas. In this case, the VSSD is performing GC, so the switch will deny GC. At a later time, when the VSSD finishes its GC, it will clear the GC bit in the table, and the second time when the replica requests and the VSSD is no longer performing GC, this time the request will be granted and the replica may proceed. Note that if the replica is running out of free blocks, it will simply execute GC without first asking. Storage devices are not always executing storage requests, so we also want to leverage that idle time to opportunistically perform garbage collection. To do that, we use a simple prediction mechanism with the exponential weighted moving average of recent idle times. If we predict that we have sufficient idle time in the storage, we will execute GC and notify the switch so future requests can be redirected accordingly. Finally, let's discuss how we can enable rack scale wear leveling. Remember that individual SSDs have effective wear leveling, but data centers have diverse workloads, and different workload instances have diverse write intensities. And this results in wear imbalances across the SSDs in the rack. Now, this can lead to premature SSD failure, which leads to increased cost and increased management complexity. To overcome this, we develop a two-level hierarchical wear balancing solution. In each server, we add a local wear leveler that periodically swaps the most worn SSD with the SSD that is receiving the least write traffic. SSDs are swapped atomically, block by block, by pausing the operations for the chosen blocks, copying the blocks to their new locations, and finally resuming the operations for those blocks. Based on our study of data center workloads, swapping every 16 days is sufficient to guarantee near optimal SSD lifetime. To ensure wear balance across the servers in the rack, we also periodically swap the SSDs across servers, but the network bandwidth is now also a concern, so we relax the frequency of swapping to once every 8 weeks. We implement RackBlox using programmable SSDs and an Intel Tofino switch, using various storage-intensive workloads. And to see its performance improvements, we compare against VDC, which coordinates across the storage and network to achieve performance isolation using a software-based token bucket rate limiting. We compare VDC with 3 variations of RackBlox. RackBlox with only coordinated I/O enabled, RackBlox with coordinated I/O and GC coordinated in software, and the full RackBlox design. We see that RackBlox reduces the tail latency by up to 4.8 times. To break this down further, we show the contribution of the storage delay to the end-to-end latency. We see as writes increase and the total storage delay increases, our coordinated I/O scheduling can get increased benefits from the increased opportunities for prioritizing requests. However, at above 80% write rates, we see that GC dominates the storage overhead and requires coordinated GC to receive benefits. We also evaluate whether or not we retain the original flexibility of SDN and SDF, and we implement RackBlox with a number of different storage schedulers that target low latency in SSDs in Linux today. And we show that their coordinated versions always outperform the original versions. In summary, we designed RackBlox, a new software-defined rack-scale storage system with network storage co-design. Through the use of coordinated I/O scheduling and coordinated garbage collection, we can improve the end-to-end I/O performance, And with coordinated with rack scale aware balancing, we can ensure that the entire rack is well balanced. Thank you very much, and I'm happy to answer questions.
All right, thank you. Okay, well, okay. I'll ask my questions after you. Okay, go first.
Thank you. Hello, Rongxin Chen from Shanghai Jiao Tong University. Good nice work. I have a question for you. How will you schedule the I/O request if your network delay is inaccurate due to clock drift?
So thank you for the question. The clock drift is not, we don't need to synchronize clocks for this. The in-network telemetry, we're computing the switching delays in the individual switches, and so there's a timestamp of, so each individual switch timestamps at the beginning when the packet queues and at the end when it leaves the switch, and so we don't need to coordinate. We don't need to synchronize clocks.
Okay, so the delay is computed totally on the switch, not the client and the server, right?
Yes, there's no need to coordinate or synchronize clocks in order to compute the delay.
Okay, thank you.
I have okay. All right, I'll take your question before me.
Hi, thank you very much. Marius Kogas, Imperial College London. Great work and very nice combination of all these different software-defined mechanisms. So my question is more in the context of how does this fit in the big picture of the data center? When you have all these people talking about disaggregation and you are proposing a rack scale solution, and we have all these lessons learned from SANS in the past, and people have been trying to convince us that this is not the right way to go.
So thank you for that question. I mean, I think with anything that it's a trade-off with right, when we designed this, we were looking at the trade-off between how much this imposes on the SDN and the SDF management, and we came to the conclusion that the level of that adding one packet header field and for the coordinated I/O scheduling, and that the level of memory that we're using in the switches justifies that kind of coordination. So I don't know that. So I wouldn't say that we have a general prescription other than that kind of analysis needs to be balanced, and for us it was then that the coordinated GC and the coordinated I/O scheduling reaches that balance in a way that is not overly onerous in terms of the burden that it places. Yeah.
All right, last question.
Thank you.
Thank you. I'm Jian from Peking University, and I'm wondering about how you deal with the packet loss in the network. For example, a packet just passed the programmable switch and updated the states in the switch, but in the SSD, it will get lost, and at that time there will be an inconsistency between the state in the programmable switch and the state in the SSD. So how do you deal with that packet loss? Thank you.
So thank you for that question. The only state the only state updates originate at the storage server, and then the storage server would detect that we didn't get the reply, and then it would resubmit that request. So that's how we would deal with packet loss. So there's nothing externally coming from other racks that would update the state that the storage servers would not be aware of. So.
Yeah. All right. Thank you.
All right, thank you. Let's thank our speaker. So we ran